In this video, I just want to generalize some of what we've seen so far. In particular, we've focused on the desire to approximate a function at 0, but now I want to consider what if we want to approximate more generally at some known point x equals a, where a doesn't necessarily equal 0. So I'm going to write down a more general definition, and importantly, this definition includes the possibility of the center being 0, but it's not restricted to that. So here we're going to say that the nth degree Taylor polynomial for f of x centered at x equals a is the function t sub n of x such that every derivative of t sub n evaluated at a is equal to that derivative of f evaluated at a, where here when I talk about every derivative, we're talking about the 0th derivative, which is just the functions themselves, all the way up through the nth derivative if it's the nth degree Taylor polynomial. So that's the key thing that we define here. What can be helpful to remember is that this function that satisfies that all those derivatives are equal can be expressed as how I've boxed it here. Importantly, notice that if I were to substitute in a equals 0, this would reduce to exactly the same formula we had before. So rather than thinking of this as an extra formula, I would just only know this formula and just keep in mind that the center may in fact be 0. So we have the same kind of structure we've seen before. With that in mind, if I go back to, we've looked at e to the x centered at 0, if I consider e to the x centered instead at 100, and we want to find the third degree Taylor polynomial, what we still have going for us here is that every derivative of this function is simply e to the x. However, the way in which that's useful to us is that when I plug in 100 to the derivatives, I'm now going to get e to the 100. So in finding the third degree Taylor polynomial, what I'll do here is take f of 100, which is, so maybe let's make this a little bit more clear. So I'm finding f of 100 plus f prime of 100 times x minus 100 plus the second derivative at 100 divided by 2 factorial times x minus 100 squared. And then finally, because we're asked for the third degree, I go up through this f, the third derivative at 100 divided by 3 factorial times x minus 100 quantity cubed. So what I can do now is just drop in what I know about those derivatives of f. So I'll put in that t sub 3 of x is equal to e to the 100 plus e to the 100 times x minus 100 plus e to the 100 over 2 factorial times x minus 100 quantity squared plus e to the 100 over 3 factorial times x minus 100 quantity cubed. So that's our final answer. And I'll point out, just coming back up to this definition here, the only thing that changes in this definition as you change your function is what I'm boxing in green here. So these are the things that we had to supply for our special situation to get the desired Taylor polynomial. And the other thing I want to point out is that the center really affects the polynomial not only in that it shifts the focus, so we before had powers of x to the k, and now it's x minus a to the k, which we envision as shifting a function over k units to, or excuse me, a units to the right. But the other thing that's important is that we need to know information about the derivatives of the function at a instead of before when we set at 0. So we're thinking of a shifted version, but also updating it so that we take into account the behavior of the function at our point of interest. And so this is kind of, like I said, our concrete example of seeing that not only did we get e to the 100 instead of 1 when we did the center at 0, but we had to change those factors to include the x minus 100s instead of just x's. So here, we want to find the second degree Taylor polynomial centered at x equals 1 for a particular function f of x. And this function is a lot simpler. It is a polynomial. So notice here that we're going to need to find 3 things. We need to find f of 0, we need to find f prime of 0, or excuse me, not 0, f, I should need f of 1, f prime of 1, and f double prime of 1. So we're given that f is the function 4 plus 3x minus x squared. If I plug in 1, I'm going to get 4 plus 3 minus 1. So I'm going to get 6. The first derivative of this function is going to be 3 minus 2x. If I plug in 1 to that, I'm going to get 3 minus 2, or 1. And the second derivative is negative 2. And if I plug in 1 to that, it's a constant function, I just get negative 2. So the Taylor polynomial that we're asked for here is f of 1 plus f prime of 1 times the quantity x minus the center 1 minus, because it's negative, 2 over 2 factorial times the quantity x minus 1 squared. So of course this is just going to reduce to a negative 1 out here. So that would be our final answer. However, I'd like to show that we can simplify this. So this is, we'll put it down here. So to be clear, this would answer our question. But we can simplify. So I've got 6 plus x minus 1 minus, what do we have in here? It's going to be x squared minus 2x plus 1. So all together, we're going to have 6 minus 1 minus 1, so 4. I'm going to have plus x plus 2x, and then I have minus x squared. So notice that this is equal to f of x. And that is because of the fact that f of x is a polynomial. So what I want to point out here is that if f of x is a, let's say, kth degree polynomial, then the nth degree Taylor polynomial of the function f of x is equal to f of x when the degree n is at least as large as k. So let's unpack this statement. First of all, I intentionally did not put a center there. Notice that when we looked at the original polynomial, we might have assumed it was centered at 0 for whatever that means, and we're asked to find the center at 1. But I could just multiply it out, and I reverted back to the same structure there. So this is just ignoring center. And this is saying, the other thing to consider here is, what is this saying? Well, think about it in this context here. This is saying that if we were asked to find a Taylor polynomial of degree 2 or greater, then we should end up with f of x. So why not smaller than 2? Well, if it was smaller than the degree of the original function, there's no way we'd end up with something that's equal to that original function. We'd be short a certain number of powers. So here, the first degree Taylor polynomial would be a linear function. It couldn't possibly equal this quadratic. And the reason we can say greater than, if I asked you to find the third degree Taylor polynomial or the fourth or so on, all of my higher order derivatives would be 0, so it would yet again reduce to exactly this here. So there's something special about the fact that we have a polynomial to begin with. And if we go back to our original goal, this makes sense. If the desire is to approximate our function by the best polynomial, and the function we're starting with is already a polynomial, it should be its own best polynomial approximation. So that's kind of verified with what we're seeing here. And then the last thing I want to go over about Taylor polynomials is the idea that, even a little bit more abstractly, as long as you can find the needed derivatives evaluated at whatever the center is, you should be able to find the appropriate polynomial. So consider this next example where I'm given the Taylor polynomial centered at 0 for some unknown function f of x. And then I'm asked to find this Taylor polynomial centered at 0 for that unknown function squared. Well, let's think about what do we know. So what we know from the fact that this polynomial is the Taylor polynomial centered at 0 for the function f of x. Well, this term here has to be f of 0 by definition. And by term, I mean that 3. That 2 coefficient has to be f prime of 0 by definition. And this coefficient of x squared has to be the second derivative at 0 divided by 2 factorial. So with that, that's enough for me to be able to solve for each of these coefficients. In particular, f of 0 is 3, f prime of 0 is 2, and because of this dividing by 2 factorial, the second derivative at 0 should be 4. So this means, so let me just document that here. We don't know what f is, but I have enough information to be able to determine this. So it turns out that that's good enough. So let's think about the function f of x squared. Let's give that a name. So g of x is the square of f of x. And we want to find the second degree Taylor polynomial centered at 0. So we need to know g of 0. But that's just f of 0 squared. F of 0 is 3, so we already know that that's 9. To find g prime of x, I can use the chain rule to get this. And again, if I now want to know what that evaluates to at 0, I have 2 times f of 0 is 3, and times f prime of 0, which is 2, so we get 12. And then finally, the second derivative of g, I can use the product rule. Derivative of f is f prime, and we're multiplying it by f prime of x, so we ended up squaring that, plus f times the derivative of f prime, which is f double prime. And so when we evaluate this at 0, we're going to get 2 times 2 squared plus 3 times 4. So that's 2 times 16. We get 32. So our answer here for the desired polynomial, maybe to avoid confusion, I'll put a subscript of g on it, is we get 9 plus 12x plus 32 divided by 2 factorial, 16x squared. So I was able to compute this even though I don't know the function g of x, because what I was given allowed me to have enough information to at least find up through the second derivative of this unknown function evaluated at 0. Which, again, the significance of 0 here is that that's the center of the original polynomial.